Hello and a very warm welcome to the second part of the tutorial on submodular optimization approaches toward data and feature subset selection. I am Ganesh Ramakrishnan, professor at IIT Bombay. In this part, we begin by first presenting approaches to data selection sketching, often invoking submodular functions. We'll then move on to active learning. Several active learning algorithms are actually built on top of data selection strategies, and several of them actually make use of submodularity. Finally, we move to a very complementary area, which is data selection for data programming. So imagine that in addition to some subset of points potentially unlabeled on which you induce labels, you also have access to rules or labeling function. What will be the best way of combining some amount of label data and rules so that we can get robust learning? We'll thereafter look at feature selection, moving from instance space to the feature space. There are methods in information theoretic feature selection, use of weak submodularity in feature selection, categorical feature selection, and so on. The final part of our talk, in the part 2, would deal with summarization. Now, summarization can be viewed as data subset selection. However, there are some unique requirements here, and there are also interesting problem settings both in the image, video, and finally text domains. Will present several of their applications. You might recap that labeling data sets can be extremely expensive. Some computations that we have done based on crowdsourcing platforms such as Google and Amazon is that, let's say you have 50,000 image data set for classification. Identification of the class labels using crowdsourcing could cost anywhere between $5,000 to $32,000. Likewise, if you had to label 50,000 large image data set for detection, object detection, the cost would range between $10,000 to $45,000. And if you had to label a 50,000 large 3D point cloud, the cost is going to be even more phenomenal. And when it comes to text, you have to spend a lot of time also parsing the text, reading the text, and therefore the cost can be higher, ranging from $50,000 to $150,000. The other issue is that you may have noise in the labeling. Now you might want to very cheaply procure labels through, say, text search or image search, as you can see in this figure. Image search might be deceptive in giving you somewhat less noisy responses, but mind you, you're looking for a ladybug image through an image search, but you probably also have got a honeybee here, and you ask for a Honda Accord, but you've also got a BMW. So this noise of different sort based on the process you have employed to get your label data set. The other issue is that label data sets can have a very long tail. There are a large number of labels, as you can see here, which have low frequency, and they are often not very well represented in classification problems. In the extreme classification literature, for example, people have come up with measures such as propensity. to basically try and counter this bias in the labeling where rare labels get typically ignored just because their instances are very few. Now, let's say we wanted to make machine learning data procurement efficient and also use of machine learning data um, efficient as well as robust. What would you do? What we identify is that the model training and validation are a cycle repeated several times. That's followed by model deployment. Now, in the data preparation, you have data labeling and feature engineering. We will certainly address some of the issues in data preparation. But even after you have obtained the labels, you have to iterate several times over the model and validation set. Um, so that's the problem of model selection. Is there a possible that we can take a subset of the training data in order to ensure that we can run this iteration several times more efficiently with some training budget? So the production system constraints are that data labeling itself is very time consuming, expensive and noisy. Feature selection has a lot of latency and memory issues in terms of storage. The model training can be very compute intensive and again time consuming. Hyperparameter tuning is extremely time consuming because it requires several iterations to the model training itself. And finally, we have the issue when the training and the deployment scenarios have some difference. The distribution shift, for example. So can we train models on these constraints without sacrificing on accuracy? This is the question we attempt to answer. So what are the components of robust and data efficient machine learning? From efficient machine learning perspective, you want to reduce the labeling cost or time and reduce the training time and compute as well. Of course, we also want to reduce the compute infrastructure. What can we do to reduce hyperparameter tuning and network architecture search time, and how can the reduction in training time reflect in better hyperparameter tuning time? We will also look at the process of procuring data through a paradigm of data programming using labeling functions or rules in conjunction with some semi-supervised learning. These are components of efficient machine learning. As far as robust machine learning is concerned, you want to reduce the feature noise, be robust to class imbalance, look at out of distribution. Yes, so there are many problems. We'll try and survey some approaches. So here are some applications of data subset selection summarily, which is quick training and inference, quick hyperparameter tuning, labeling from unlabeled data, the elements of active learning here as well as semi-supervised learning, and finally robust learning. So here's the setup. We assume that the parameters theta characterize the machine learning model. We have a training data set U and a validation data set V. The loss, for example, the likelihood function could be evaluated either on the training data set U, in which case we use the subscript T. So mind you that T corresponds to the label data set U, the subscript T. The subscript V corresponds to the validation data set. So the likelihood function can also be measured on the validation data. Typically the theta optimal parameters you would estimate on the training data using the label data U. And in general, we're looking at the goal of selecting a subset of the labeled data such that the resulting model performs the best. Now, how do you factor in the likelihood or the loss function on the validation data in conjunction with the objective on the training data? I mean, this is what characterizes the different approaches. The challenge is as follows. Let's say I have to identify a subset of U and U has n elements. We know that the number of possible subsets of U is 2 raised to n. Well, we might design a good function, and by good function we mean say submodular function as discussed in the part 1. So a submodular function makes the search over this space of subsets efficient with some reasonable approximation guarantees. The issue is as follows. We are not only dealing with the subset selection. The subset selection has to interleave with the parameter estimation theta star over the log likelihood function, for example. Now, if we were to attempt a closed form solution for theta star and then go back and subset, the going back and forth is actually going to be extremely time consuming. And hence, even if training on 10% subset gives you 10x faster training is a lucrative proposal, we want to make sure that the subset selection has negligible time complexity, because ultimately it's going to have some wrapper involving the parameter estimation. Also, it's interesting to see if there are theoretical guarantees of subset selection algorithms in the context of machine learning, where we have parameter theta stars to be estimated as well. So we begin with a very vanilla approach, which is use submodular functions as proxy functions for data subset selection. And this has been, of course, finding a lot of use both practically and from the machine learning perspective. Interesting analysis has also been done. So given a ground set V, you have a set function which measures how good the subset X is, and as we have seen, the optimization problem of maximizing fx subject to the cardinality constraint has a greedy algorithm with a good approximation guarantee, 1 minus 1 over e when f is a submodular, and in practice we do even significantly better. Often you land up getting close to the optimal solution. And when f is a dispersion function, we can attain a half approximation factor guarantee. Now several papers have used proxy submodular functions, specificity location, which is submodular, feature based functions like weighted set cover functions, which are submodular, and then of course you can have dispersion functions, log determinant, which is also submodular. Now, are they the right models? Well, interestingly, experiments have shown diminishing returns, and these are across a whole bunch of papers, and we find the same trend, diminishing returns. So hence it just makes sense to use submodular functions. Can we move beyond submodular functions as proxy and see what can be done with the actual objective itself? Can that be submodular? So we'll study 3 approaches which are reasonable data selection approaches and show that they naturally induce submodularity. So we move now to approach 2. Here we try and choose a data subset which approximates the gradient of the entire data set. In this, we also factor in weights. So let's say a subset xt has a point I with weight assigned wit. The gradient of the loss corresponding to the ith point is li. This is needless to say on the training data set, that's what you see as the subscript capital T. What we would like in this setting is that the weighted average of the gradients of points belonging, gradients of the loss for the points belonging to the selected subset approximates the gradient on the entire data set, and this is the full gradient on the right hand side. Now why is this interesting? Well, this characterizes core sets, the set that you identify xt. We now look at conditions for the convergence of either the full training loss, in which case the L generalized in the expressions below will turn out to be LT, or validation loss in which case L will turn out to be LV. So the convergence result shown here will help provide a strategy to select the weights, WTs and the subsets XT, which in turn will influence the parameters theta t. So the idea is that the upper bound of the minimum of difference of losses evaluated at theta t and theta star, where L theta star is a desired loss. This upper bound has two terms. The first one is based on the rate of change of the trading data, basically an upper bound on the training loss error, the gradient of the training loss error. The second term, which is the sum of the errors with respect to the individual epochs, indicates that an effective data selection should try and have this low value of error. And what is this error basically? Well, this error, it's basically a non-difference of the weighted sum of the gradients on the selected subset XT from the full gradient. Now the full gradient could be either the validation gradient or the training gradient. So for example, if the goal of data selection is to select a subset that approximates the full training set, you will try and minimize this error with L set to LT. Else you will look at L set to LV if you want to select subsets that approximate the validation set. So this is a very general recipe, and as we will see, for some interesting algorithms, the dot product between the training and the validation set gradients also become very important. The theorem indicates that an effective data selection algorithm should really try and have this error minimized. So this is another way we can basically now pose the problem as, which is given a cardinality constraint on the subset X, try and estimate the parameters WT and also identify the subset XT such that the difference of the weighted sum of the gradients on the subset from the gradient on the entire set L is as low as possible. So one of the algorithms published in 2020 called Craig is actually derived as an upper bound to the error that we discussed in the theorem. And this upper bound is basically a facility location in the following sense. So if you apply the triangle inequality to the summation with a particular assignment of weights, and what are these weights? So basically you imagine that you're assigning every element I to an element pi t I. So in the specific example, if this is an I, the cross is the corresponding pi t I that it is assigned to. So the pi t I's are the representatives for the I's. If this is the assignment, and if the WJ's are basically the count of the number of the I's that were assigned to an element J. Under this condition, we can apply or rather expand the summation over I in X of Wi times the gradient LTI theta t as a summation over all the elements in either U or V based on what W is said to be of this gradient. So now what we have done basically is take the summation outside over all the elements in W, and the second step is we apply the triangle inequality, where we take the norm of the summation to be less than equal to the summation of the norm differences, the norm of the differences. Now this can be shown to correspond to the facility location. Well, you'll have to of course not look at the minimum but the maximum, but it suffices to understand that basically what you have obtained as these the assignments of pi i's is the k medoids, and what you have is a k medoids problem is an upper bound to the original error. So this is the k medoid problem. We can similarly formulate the maximization version, and then you will find that the function is exactly, the lower bound is exactly the facility location function. So maximizing the facility location function in the maximization version under the cardinality constraint that the number of these points in xt is say less than equal to k. Now this turns out to be a constraint submodular maximization problem, for which, as we have seen in the first part, there are efficient 1 minus 1 over e approximation algorithms. So the Craig algorithm optimizes a facility location based upper bound. Now as a result, Craig based on facility location based data selection could require larger subset sizes to achieve some desired epsilon error in the gradient difference. Can we do better by directly optimizing the error term as in here? And it turns out that we can. So we directly optimize this error function with a regularization here, which gives us also some strong convexity. We could also convert this into a maximization problem. So imagine that you have these E lambda x minimized over W, and if we defined an F lambda x as an L max, as we have heard in the first part, this is an equivalent function which you could equivalently maximize. So F lambda x can be shown to be approximately submodular, and it basically admits an 1 minus exp of minus gamma approximation guarantee. So the greedy algorithm obviously on F lambda x can be very appealing. However, it turns out that it needs to compute the gain of every element j with respect to x order nk number of times. K is the budget and n is the number of elements in the set. So this can be very computationally expensive. Therefore, instead of greedy algorithm on this F lambda, we have an even better proposal which gives us actually similar result, and that's the OMP algorithm, orthogonal matching pursuit, which is run with a cardinality constraint mod of x less than k. You could also run it with a slightly different error constraint, but let's say that for the time being we look at the cardinality constraint, and that basically returns this 1 minus exp minus gamma under the cardinality constraint. What is the algorithm? Basically you're looking at the error. Now initially of course you have not added any element, so you just have the second term, depending on whether you have used W to be the U or the T validation set or the training set. Now what you do is look at the projection of this error term for each element I in that set W. The projection is measured along the gradient of the loss with W, which is U or V. You choose that element I with whom the projection is maximum and add that element to X. So this is for every element I in W. Now having added that element, so please note that you're not solving E lambda and then computing F lambda. You're basically now adding elements incrementally. For the new element that is added, you find the WTI for all the elements that have been added so far in X. Now you compute your new error term R. Now from 3 you go back, you have a revised estimate of R. Again compute that element I in either U or V, which has the highest dot product, yields the highest dot product with respect to the complete data gradient, and again choose that I which has the highest projection, add it to X, use linear regression which can give you closed form solution. Keep doing this until one of the convergence criterion. Now if mod X is less than K, we already mentioned that we get an interesting approximation guarantee, 1 minus exp 1 minus gamma, which is what is given by the virtue of approximate submodularity. Now it turns out that this is one way in which the dot product influences, the dot product between the gradient influences the algorithm. We'll see another way in which the dot product between train and validation gradient influence convergence. So we move on to this third approach, where the goal is to choose data subset that approximates the performance of the full training data set or possibly validation set as a bi-level optimization. So here's the bi-level optimization. You are measuring the loss on the validation set, estimating parameters theta on the training set. Now we have very explicitly defined the roles of both the training and validation set. However, the loss on the validation set should be minimized with respect to the subset S of the training set on which the parameters theta have been estimated. So S has influence on theta. Therefore, the idea is that you want generalization, generalized performance on validation set, find the right subset of the training set that gives you the best generalization. Now it turns out that the inner problem has a closed form solution in the case of several simple classifiers such as naive Bayes, nearest neighbor, or linear regression. Specifically, in the case of naive Bayes, you have a log likelihood function, and that maximum likelihood parameters turn out to be very simple closed form expressions, and under certain assumptions such as some cardinality constraint and the fact that the classes are balanced, the data is balanced across all the classes, your log likelihood function is a feature based submodular function, monotone submodular function of the set. So therefore you have efficient greedy algorithms which are also effective. Likewise, for the nearest neighbor classifiers, again you get closed form expressions, and the parameters theta, once they're obtained in a closed form expression, the likelihood function turns out to be a facility location function under some similar simple assumptions on the class priors. However, um, this is not necessarily acceptable to us because the solving the inner optimization problem even in closed form um, will still entail solving the outer optimization problem several times for every subset that you select. So it basically defeats the purpose of selecting a subset for faster training. And also we want to generalize beyond the losses mentioned in the previous slide, such as you know linear regression loss, least squares loss, that is, or the nearest neighbor and naive Bayes losses. So for these two reasons, you would like to see what more can be done. Can we interleave the solving of theta with the subsetting of x? So is there a way that the outer argmax problem and the inner argmax problem can be interleaved for overall efficiency? So here's one step towards that, which is an online one-step meta approximation, where we approximate the inner optimization problem by taking a single gradient step. As you can see, this is a single gradient step toward the training of the subset log likelihood ascent, right? So the substitution of theta star in the outer optimization problem in terms of this one-step approximation gives us this new optimization problem. Now, how do you solve this? What do you do? So note that there exist log likelihood functions LLV and LLT, and basically corresponding training and validation data sets, such that this equation, the optimization problem here, is NP hard. However, if the validation set log likelihood is either negative logistic loss, or negative squared loss, or negative hinge loss, or the negative perceptron loss, this is reasonably wide variety of loss functions that get employed in real world machine learning. So in all these three cases, the optimization problem becomes an instance of the cardinality constraint submodular maximization problem, which means you have 1 minus 1 over E approximations for the greedy algorithm. Also, if the LLV turns out to be a negative cross entropy loss, even then we have submodularity, but we have weak submodularity with approximation guarantees that have been already discussed. Now, why would we want to go further? Well, it turns out that if you have to employ the greedy algorithm in either of these either of the cases, to compute the gain for every element E given a particular current configuration, say Sk. So you're going from Sk, select the E and go to Sk plus 1. But for this, to compute the gain, you will actually have to compute the log likelihood on the validation data. This can require several forward passes, especially if the network is a deep network. This can be very computationally expensive. So if you employ a Taylor series approximation on the validation objective here, and what have we done? Basically, we have taken only the first order approximation. We have restricted ourselves to LLV theta plus the dot product between the gradient of LLV at theta with the second component of the argument. So this obviously, this dot product is going to be interesting going forward. We have already seen that alignment between the validation and training data sets can be very important in general, and we're going to see that in our convergence proof. Now it turns out that with this, all we need to do with this first order approximation, by ignoring the higher order terms, we will only need to have k forward passes for calculating the validation log likelihood corresponding to the budget, and we'll also have additional k backward passes to compute the validation log likelihood gradient. The backward passes are required for the gradient. Now we can further reduce this. While this itself is useful, it turns out that instead of computing the log likelihood k times, we can and the forward passes k times, we can use stale likelihoods and compute the validation log likelihood only r. So this is precisely one of the engineering tricks we use, where we recompute the validation log likelihood only r times instead of k times, and use stale log likelihoods for the k by r greedy steps. In addition, we also try other options, which is stochastic greedy selection. So stochastically select an element greedily. Also, we consider other optimizations, such as avoiding selecting the subset every epochs, but select rather the subset every k epochs. Every L epochs. And further, in deep networks, we may use only the last layer gradients during inner and outer optimization problems for subset selection. We also have tried different regularizations on top of our algorithm glister to prevent overfitting. And examples are facility location and random regularization. The idea is to at least not do worse than facility location or the random regularization, and therefore in that way prevent overfitting. So this is the overall strategy, where we initialize with random parameters and a random subset. You have L epochs of stochastic gradient descent on S0. That gives you a theta L. Now you do a greedy data subset selection with the Taylor approximation, and you get an S1. And now basically you're going to apply L more epochs of stochastic gradient descent to get theta 2L, and so on. Now, what about convergence properties? And now for the convergence analysis. So if you basically ensure that the validation loss function LV is Lipschitz smooth with some constant, and the gradients of training and validation losses, their norms are bounded by some sigma t and sigma v respectively, then the validation loss will always monotonically decrease with every training epoch. Now you can also show that there is a convergence order of 1 upon epsilon square number of epochs convergence. If you assume that the dot product of the validation and the training loss are always greater than or equal to 0. And there's this delta min, basically, which is the minimum of the normalized values of the gradient, normalization with respect to the norm of the gradient itself, the upper bound and the norm of the gradient. Then there's this interesting result that the minimum of the deviations of the loss from the optimal loss is upper bounded by a term which is 1 upon square root t, which is what gives you 1 upon epsilon square epochs. And then there's this additional term now what is this term? It's basically involving square root of 1 minus cos theta, where cos theta is basically the dot product of the gradient. Now we remember that Taylor approximation chooses a subset that maximizes the dot product between the gradients of the training loss and the validation loss. So we expect that the angle between the subset training gradient and validation loss gradients will be close to 0. So therefore we would expect this value to be roughly or tending to 1. Now the delta min must be greater than 0, which is also reasonable. It's reasonable because having close to 0 gradients on the subset gradient set would imply overfitting on the training loss. So we would really not like to overfit, and then so this way we can justify different elements of this convergence result. The fourth category of approach is selecting data subsets by minimizing a divergence, and Shinohara et al. In 2013 motivated this problem for sentence set selection using features. So the motivation is to view the data subset selection objective as minimizing some KL divergence between the original full data distribution and the subset in the feature space. So the MUX is the maximum likelihood estimate based distribution on the feature set U, and with respect to the full distribution. In practice, you can use any of the submodular models such as representation, coverage, diversity, etc. as proxy functions for data subset. As a first application, we evaluate the efficiency of our subset selection methods to enable learning from lesser data, yet incurring minimal loss in performance. So here are results. For example, the first application, k nearest neighbor classification, the face and gender data sets. So as hypothesized, using only a portion of the training data, say even 40%, as you can see, we get similar accuracy as with just using the entire 100% data. Moreover, we observe that facility location performs much better than random sampling. So this is facility location at 40%, performing much better than random sampling, and also better than disparity min, which is the one in red here, proving that facility location is a good proxy for nearest neighbor classifier. So this kind of reinforces connections between different objectives and a submodular function here, for example, facility location. We see this both on gender recognition and face recognition data sets shown here. We also have some interesting results with Glister when we use the validation data for generalization. So we basically see that Glister achieves a 7.2x speed up at just 10% data subset, 3.5x speed up at 30% and 2x speed up at 50%. So obviously with decreasing speed up and increasing data set, we do find that the accuracy gap decreases, but the accuracy gap even with just 10% data set with which either 7.2x speed up isn't really that high. It's just 2.5% for CFA 10. On MNIST, we find that Glister achieves a 3x speed up at 10% while losing only 0.2%. So there exist several data sets where the speed up is significant, because with a smart selection of a subset for generalizing on validation set, you hardly see any accuracy drop. Here are results on robust learning. What happens if there's a class shift, class distribution shift, or this introduction of noise? So we find that even in these settings, Glister can perform even better than the full data, and that too by a significant margin, 15 to 20% in terms of accuracy. This is of course in both class imbalance and noise settings. The results are evident here. You can see the significant improvement that Glister has. There are of course now different Glister plus facility location as a regularizer, whereas on the right hand side it's just Glister without the regularization. So how about data subset selection for hyperparameter tuning in settings outside Glister? And well, there are very interesting observations. You're able to select typically 5 to 10% of the entire data, and therefore it's much easier to tune the hyperparameters on the subset. So we notice that facility location function generally has positive gain compared to random, and except for one of the hyperparameters, disparity min also beats random. So we observe that hyperparameters chosen by facility location obtain the best result, which is 10.5% improvement in the top 5 accuracy compared to the hyperparameters chosen by the random set. And how about unsupervised data subset selection? This is another application where we look at the problem of labeling massive data sets, specifically when the data comes from videos. Videos can have a lot of redundancy. It doesn't prove effective to end up labeling even the redundant data. So the data here is unlabeled, so we need to apply unsupervised data subset selection, and we achieve subsets of various sizes using unsupervised, say, video summarization. Compare the results to random. We see that disparity min has the best results, followed closely by facility location. Both these methods achieve almost 5% improvement compared to random subset in terms of mean average precision. Also, diversity is more important here compared to representation. We now move to the next application of data subset selection, which is active learning, specifically diversified active learning. To begin with, we'll assume that in diversified active learning, we have a warm start, which means that we have reasonable amount of label training data based on which the estimated uncertainties are reliable. And therefore, based on these reliable estimates of uncertainties, we are able to query from the unlabeled pool to find the uncertainty of example, class uncertainty of examples X, maybe possibly sort them, and let the oracle assign label to those uncertain examples. Now, what would you do? Pick the most uncertain samples to label. For example, pick the ones with the highest value of entropy. Entropy is a modular function. However, we realize that in practice the human labeler labels data in batches, not individually. So if they've been selected in batches, would we like redundancy? Why not pick maybe diverse yet uncertain instances to label? And diversity could be measured through DPP. Um, you would also like to ensure that these instances are high coverage, that's they cover different aspects of the distribution. So high coverage you could ensure um, using say facility location, or you could even look at feature coverage using weighted set cover. So for multiple reasons mentioned here, it makes sense to have diversified active learning look at the set of instances instead of looking at an individual instance. So here's the first step, filtered active submodular selection. As expected, the first step would be uncertainty filtering, remove data that the system is already certain about, and as I've said before, this is what we refer to as Worm's start setting. The system's certainty about instances can be assumed to be correct, and thereafter we have subset selection on the examples to be labeled. The difference is that because we don't have the labels, we will use hypothesized labels on the F so that you get diverse and possibly representative subsets selected. So this is called filtered active submodular selection, and we compare results on object recognition, face recognition, and scene recognition data sets as well. There are many classes, especially in the latter. When there are more classes, we find facility location giving better results. Diversity works better than representation, particularly when the size of the data set is small. For two-class classification, there is a lot of similarity in the data set. For example, there is more than one image for the same person. In that case of two-class classification, it's not surprising that diversity works well. In each case, we see that subset selection algorithms, when executed on top of uncertainty sampling, outperform vanilla uncertainty sampling, and of course random selection as well is outperformed. Moreover, the effect of diversity and representation reduces as the number of unlabeled instances reduce, in which case uncertainty sampling already works well. In practice, that would be the point where the accuracy saturates as well. We also looked at influence-based sampling. What if you measured the impact that a selected unlabeled example with possibly imputed labels would have on the overall accuracy and likelihood of the classifier that's being learned? Obviously, it would be difficult to find closed form expressions. You can only look at influence in an expected sense as mentioned here. And we also have looked at approximation schemes for quick computation. But in general, we find that there is a lot of value in looking at influence-based sampling. Kind of also reinforcing that uncertainty by itself may not help capture diversity and representativeness. The second approach is based on an interesting upper bound on the empirical risk, and the upper bound has this first component in terms of the red dots, which is a train error, and there is a component involving these points in blue which form the core set. So this gives you the core set loss, and it turns out that this problem is equivalent to picking a set of data points. The problem of minimizing the upper bound is equivalent to picking a set of data points which maximizes this interesting objective, which is basically a robust version of facility location. So what you do in facility location is that you have a sum, and here you have a max, and that's why we call it a robust version of the facility location objective. The problem is also well known as the K-center problem. So you need to pick the green points such that the maximum distance of a red point to a green point is minimized. So that's a criterion for picking those green points. Now it turns out that this is not submodular, but closely related. In fact, the greedy algorithm gives you two approximation. So we clearly observe the significant advantage that core set algorithm yields over most other state-of-the-art, and there's a domination for a reasonably large number of labeled images as they are picked. Other approach to subset selection for active learning is kind of a variant of Craig. Recall that Craig minimized an upper bound to the minimum value of the sequence of loss differences with respect to the optimal loss, and this upper bound was basically the normed difference of the weighted average of gradients computed on the subset selected with the difference with respect to the full gradient computed over the entire training or validation set. Now batch says, well, instead of assuming that the labels are known, let us impute the labels or have the labels determined using the currently trained classifier. So the idea is to pick a set of examples with diverse gradients, very much like Craig. Now, if you use facility location as a diversity function, it turns out to be very closely related to Craig with, as I mentioned earlier, using the imputed or guessed labels, where the guessed labels come from the classifier trained so far. However, Craig did something more which Batch doesn't, and that probably makes leaves some scope for improvement for Batch. So Craig further looked at an upper bound, assuming that the loss is convex, and this upper bound turns out to be actually nothing but a weighted feature function difference. So feature function on the subset versus feature function on the entire set. And that makes Craig more efficient. Badge is also related to filtered active submodular subset selection, but unlike FAS, which required uncertainty filtering, Batch doesn't require uncertainty filtering. Actually, picking diverse gradients ensures uncertainty and diversity together, which makes it a much more holistic approach. And we later on show that the Glister algorithm that was discussed earlier actually has several of these advantages when it's improvised for active learning. And here are results again with batch with diversified gradients. Um, Back then, certainly batch had an edge over the state of the art because of its overall holistic approach, though computationally it probably is a little handicapped. Accuracy wise, you do find that um, it maintains a consistent lead over the state of the art then. The state of the art then include entropy based, of course random, and some existing core set algorithms then. So core set is basically a diversity based approach where the embedding of each example is computed by the network's penultimate layer, and the samples at each round are selected using a greedy furthest first travel condition on all labeled examples. Conf that you see here is an uncertainty based active learning algorithm that selects a batch of examples with the smallest predicted class probability. Marge is an uncertainty based active learning algorithm that selects the bottom B examples sorted according to the examples multi-class margin, so based on margin based classifier. Entropy is basically an uncertainty based active learning algorithm that selects the top B examples according to the entropy of the examples predictive class probability distribution. So effectively it's based on a modular function. ALBL is active learning by learning. It's a bandit style meta-active learning algorithm that actually selects between two of the algorithms, which is core set and conf at every round. So you could think of it as a kind of ensemble in the active learning sense. And rand is the naive baseline where you select the random k examples to query at each round. Our core set is obviously coming reasonably. I mean, it's performing really reasonably well in the two cases, A and C, but pretty the OpenML data set, you find that the performance is quite pathetic. In this approach number 4, selection via proxy, the idea is that you train first a trimmed down or a proxy version of the overall model. This is used to estimate the utility of individual training data points. Select the most informative ones for training the large target model. In fact, you can have multiple levels of proxy, as you can see here. So the proxy is basically a scaled down version of the target model, and you can have multiple such scaled down versions. The idea throughout is to basically select examples in decreasing order of their uncertainty. Now they use different notions of uncertainty. 1 minus the probability of a class, or 1 minus the min probability of a class. They also look at entropy. Interestingly, they have shown up to 1.6 times to 1.8 times speed up on CFAR10 data set by just selecting 60% of the subset of the data. Approach 5 is an improvisation of what was discussed earlier, subset selection using Glister. This is called Glister Active. The idea is very much like a badge, which was kind of an improvisation of Craig. Here we select a subset of points every epochs to be labeled and add it to the current labeled set for model training. So like badge, the use is made of hypothesized labels for unlabeled points during the inner level optimization, which was discussed at length earlier. And after each subset selection, this model is trained on the label set for L epochs before the next subset selection. On a number of data sets, we find that Glister Active perform better than state of the art, which includes Batch. Of course, Batch is a stiff competitor. However, Glister Active also has the advantage of computational efficiency. So we do find that F-Glister in one case and in the other case D-Glister have been doing well. But what characterizes Glisters also is computational efficiency. We move on to the last part of this data subset selection and active learning, and this is about use of data programming and some amount of semi-supervised learning. So suppose we had multiple labelers. These labelers could be rules. It's also possible that some of them are humans or weakly trained classifiers based on small amount of human labeled data. Now what we find is that with multiple labelers, if you had multiple labels as well and little or no training data, it becomes very important to estimate labeler reliability. One simple idea to estimate labeler reliability would be to look at the divergence of a labeler from the majority label, and you can intuitively guess here that labeler C seems to be all over the place, at least in the first domain, and in fact it's all over the place even in the second domain, and labeler B is probably not very well equipped with this first domain, which is of clocks and gauges. Labeler A on the other hand seems to have reasonable reliability. It seems to be kind of determining the majority score in many ways. So it's possible that labelers also have complementary expertise. Can they mutually benefit from their individual expertises? So that we can come up with better consensus models. Coming to active learning, what are the examples on which the labelers seem to have high divergence? So that by introducing these examples, for example the one here, the clock and gauge, there seems to be too much confusion even with a more reliable labeler A. So should these examples be labeled and therefore complement the labeling function or the rule to overall result in a very effective and high quality label data set. We also want to ensure that we are minimizing the overall labeling budget. So we don't want too many examples to be labeled here. So this is an area that's being developed, data programming and in conjunction subset selection. So what we want to do is not just develop consensus amongst the labeling functions, but also identify the subset of examples to be labeled, so that as you can see in this figure, there is this feature based function F, the consensus function, and then there is a rule or the labeling function based consensus model G. Now you would like the F and G, or the theta based estimation, the parameter based estimation and the labeling function based estimations, to agree well on both the labeled and unlabeled data set. And certainly you would like that on the labeled data set the features are learnt reliably with low entropy on the unlabeled data set, while also agreeing on the unlabeled data set with the feature-based prediction function, agreement between the feature-based prediction function and the labeling function based prediction function. So of course this the labeling functions themselves need not be always discrete valued, they can also be continuous valued. That's something we reported at IIII 20, and we also explored important models of consensus in our IIII 18 paper. And more recently we've been looking at this combination which you see here, combination based on both labeled and unlabeled data, and that's the work being referred to here. We now move on to the second component of part 2, which is feature selection and compression, which has also seen the use of subset selection combinatorial problems and specifically the use of submodular functions. We begin with information theoretic feature selection, move on to weak submodularity in feature selection, categorical feature compression, and finally learning to compose features combinatorially. So first, feature selection. Often the feature space, as you see here in this example of text, is such that the operations of X following Y which to form phrases is not really commutative. So how do you find compositions of these basic features in a very large search space given certain constraints on the compositions? So the feature selection framework typically is that you generate a subset, look at the learning algorithm, evaluate the performance, go back and generate the next subset. This of course assumes that obtaining the features is itself possible in reasonable time, but maybe in certain domains such as medical domains, a feature obtaining itself could be a costly affair. So there are two issues here. One is how do you save on the overall search space exploration so that at runtime we can save on prediction time and model size becomes compact. And the second is yes, the often construction of features itself can be expensive. Several natural feature selection frameworks actually do involve submodularity. So one of the first approaches in this space of generate and test was based on mutual information. Mutual information is often used for feature selection itself. Now the mutual information I is unfortunately not always submodular. However, if all the xi's are conditionally independent given the y, then FA, which is characterized by the mutual information xa comma y, turns out to be submodular. This is fairly intuitive, right? Information never hurts. And then there's of course a saturation with respect to information as you keep including. So this is kind of hinged on the naive Bayes assumption. Now often you don't have the naive Bayes assumption, but even when that I is not submodular, it is showed to be the difference of submodular functions. Even with this, estimating the MI can be difficult when we have very large feature sets. Let's say you need to explore and construct those features. Hence, many mutual information based feature selection frameworks approximate the mutual information by breaking it into two parts. The first is the relevance, and the second is the redundancy. And the idea here is that you want to maximize the relevance and minimize the redundancy. Therefore, the object is often called MRMR. MRMR is almost like the graph cut, and the MRMR algorithm is an approximation of a theoretically optimal maximum dependency feature selection algorithm that maximizes the mutual information between the joint distribution of the selected features and the classification variable. So this is basically just an approximation of what we had set out to maximize. As MRMR approximates the estimation problem with a series of much smaller problems, each of which involves only two variables. As you can see here, there are only two variables involved in the series of problems. It uses pairwise joint probabilities, which are more robust. And it is found to perform a very effective feature selection even with this MRMR approximation. Recently, Das et al. Worked on cost-aware feature selection. And the setting is that instead of one generic set of features applicable, say, to all patients, can we have a clustered approach for feature selection? So, using observed features, you could just cluster patients into groups. Now, in the training data, you could be given demographic information that could be used to cluster patients into groups. These are basically patient clusters. And as already stated, possibly different features may be relevant to different people. So now on the patient clusters, you use the mutual information feature selection module and perform joint training. Basically, you again use MRMR. There's an additional component here where you're also concerned with the cost. So there's a cost-aware feature selection. Some tests for patients might incur cost, and it's not necessarily cost in terms of money, but it may also have other side effects. So, and that's exactly where the patient clusters based on observed features helps determine correlation of feature sets with patient groups. So for certain set of patients, certain features should not be even considered. Another approach is to maximize a loss-specific objective for finding the right subset of features. For example, in linear regression, can we find a subset of features A such that the resulting model has, say, the highest R-square measure? Now, R-square has been studied by Das and Kempe, and they found basically that the log likelihood, which generalizes the R measure, is weakly submodular if L is restricted, smooth, and strongly convex. The notion of weak submodularity implied by Das and Kempe basically involves a submodularity ratio. The submodularity ratio is roughly the ratio of the sum of the marginal gains obtained from the elements in a set, say S, with respect to the gain with respect to the entire S itself. So it's intuitive that this ratio, if it's greater than or equal to 1 for every possible subset, only then we can treat the function to be submodular. And it turns out that if for some weak submodularity defined in terms of the submodularity ratio, you can actually come up with data dependent bounds for approximation, basically gamma dependent bounds for approximation. So this framework generalizes orthogonal matching pursuit and forward selection algorithms. We did talk about OMP earlier in the tutorial, and thanks to weak submodularity, since f is monotone, we get an approximation guarantee of 1 minus e raised to minus m by capital M. So the small n and capital M, for those familiar with um, analysis of algorithms for strong convex function with smoothness assumptions, these basically are the restricted strong convexity and restricted smoothness parameters respectively. Bettini et al. In 2018 looked at another very interesting variant for feature subset selection, but this was in terms of categorical feature compression pivoted on this function f. F is a function that takes in, say, feature such as China or Japan and maps them to a single category C1. So the purpose served by F is basically that of mapping the feature column into a more compact set, which is the compressed feature set. You can think of these as clusters. Now you want to maximize the mutual information of this, not feature selection but kind of feature compression on the set of features, maximize the mutual information with a with some given classes. For example, the favorite fruit, which could be what the class C corresponds to. Now this problem, though it appears interestingly complex, it's actually possible to reparameterize as a submodular function, and there's a quasi-linear time algorithm which achieves a 1 minus 1 over e approximation. Also, Bettini et al. Showed that it's possible to achieve a distributed log n approximation. Now, there has been significant work that has looked at learning compositions of features efficiently. For example, let's say we're trying to learn model for classifying cars based on both simple Boolean features such as sales and price and a couple of other features, LS, BS, etc., and their combinations, which is characterized largely here through conjunctions. Can we learn to compose these basic features as conjunctions to create interpretable rules, weighted rules with associated weights wi's, such that the resultant classifier is accurate, which means you either using hinge laws or some logistic laws, you maximized and not only obtained the weights and the rules, but also obtained the combinations of the basic features that created those rules. Now it turns out that you're actually searching a large search space. Now the search space can get even more complex if you're looking at, say, patterns, not just conjunctions but sequences. So selection of contiguous patterns in a sequence. In most settings, the search space can be written as a lattice. In the case of a conjunction you have commutativity, but in the case of sequences you don't have commutativity. So when you have conjunctions, it's possible to write, say, the sum of product as product of sum. You won't get those privileges when you're looking at contiguous sequences. In general, the idea is, given a large lattice, you want a subset of nodes in the lattice which correspond to really these compositions of those atomic features, such that you do well on an n classification task. So what are the tools that really make this possible? Supervised subset selection of lattices. Now it's possible to use block norm regularizations to basically get sparse combinations. So you may want only a small number of such rules. Moreover, you may also want each of the rules to be compact. So you look at convex relaxations via L1 LP block norm regularizers with a L1 norm over individual block, and by block we refer to let's say all the descendants of a particular node. It's called the descendant norm. So if you have an L1 norm on the entire descendant block, then you get sparse set of descendant blocks. You may additionally impose sparsity within each block to kind of ensure that you get compact rules. So there are efficient mirror descent based active set algorithms on the dual with efficiently computable subdifferentials. This has been generalized to multi-class, multi-label, and also multitask. And yes, there's also been work to address, say, disjunctions, conjunctions, sequences of propositions, and in general first order logic under some important assumptions such as decomposability, and also sequentially structured output spaces. A lot of this has been made possible also by submodular minimization via the LOAS extension. Now move on to the final part of this presentation, which is video, image, text summarization. We begin by providing intuition that underlies most of the summarization models. The idea is that you want to summarize a large collection of images or text documents such that the summary has diversity, coverage, and representation. Often you want to bias the summary based on some query, so you want elements to be relevant to the query. You may also want privacy preserving summaries, in which case you want to hide the query. One of the classic use cases is image collection. Let's say you have a large album and spanning multiple years, multiple trips that you have taken, based on which you have taken the images, and you may want query based. Let's say I want all images that are on beaches. I may in fact also want the other way, which is privacy preserving. I don't want images which have some private information. In video summarization, the flavor has been slightly different because you also are interested in sequences of shots. So nevertheless, the flavors of generic summarization and query based summarization remain. There's also this entity based summarization where your query is not really a keyword, but it could just be an entity. For example, get all the faces in a video. So this is more about certain object categories that you want to retrieve. Here you often fall back on redundancy across the frames. Third application is news summarization, lots of news articles. You may want a normal summary or summary specific to a query say Trump or coronavirus, or you may want queries that ignore topics, issues that you're not interested in. Now, the common approach underlying all of these is feature extraction to begin with. And then you instantiate some submodular function, one of your favorite similarity-based, coverage-based, feature-based functions. Invoke the summarization algorithm, which could be budgeted summarization or coverage summarization, which we have already discussed. Now, to give an idea of how the summary is influenced by measures such as representation and diversity. So consider these images. If you're only looking at diversity, something like the points here 4, 9, 1, 2, etc., which are really outliers, get picked up. Whereas if you want representation, you really try and cover all these clusters, but it might happen that you land up missing out isolated points, which should be also covered, which is actually the case. There are lots of isolated points. So this is where there's a trade-off. You probably want a combination of representation and diversity, as we have always wanted in other subset selection instances. So we want a criterion that helps identify a combination given some training set based on which the combinations can be calibrated. Now here's another example. Let's say we want to highlight the importance of representation here. For example, if you were to just select frames based on diversity, you'd probably get very spurious frames such as the one in the end, a concluding frame, which has no information whatsoever. Coverage functions, on the other hand, are trying to do feature-based coverage, and therefore probably get you meaningless frames, just because in toto these meaningless frames have good coverage of the features. This is exactly where representation can step in. Of course, representation with some amount of diversity and coverage, so you can kind of guess what the frames would be that would get selected. I mean, something like this, and some frame like this, which basically captures 2 people and 1 person, and so on. So you're trying to get representative canonical subset. Now, as far as video summarization is concerned, there have been specific approaches to get diversity that also looks at sequential information. For example, sequential DPPs for video summarization. There have also been KDPPs, which have been used for image summarization, improvised for video summarization, basically by conditioning a standard DPP on the event that the set has a cardinality K. Of course, there are complexities that arise because of this, because you have marginal probabilities that the K gives rise to. The ensembles directly model the probabilities of observing each subset, which offers a convenient target for optimization. Here you can see the effect of including representation. You find that that's very represent or useful for TV show summarization. For example, for another use case, surveillance. Now, surveillance, you would probably want to look at diversity more, and that's exactly the case, because if you were to look only at representation and coverage, you would not find the anomalous cases, the outliers, which probably are the most important set of frames to discover. So what would disparity min correspond to? Diversity, that's in the case of surveillance. And here you find that facility location, which gets you representation, is a bit redundant, whereas the disparity min, which gave you diversity, uh, gave you maybe a frame where there was no one present at all. You can also do object-based summarization, in which case, disparity min might give you false positives, just because you're looking for arbitrary diversity, as is here. But facility location, on the other hand, is trying to be representative of different kinds of faces. Let's say you want to do face-based summarization, and therefore might be a default choice. However, coverage might be even more useful, because you want to not just get representation, but ensure that even several tail faces, or rather faces which are very less frequently observed, and as you can see here, there's a serious some of these poses are not captured in the facility location, but they are captured through coverage. Coming to the next part, image collection summarization. The work got initiated by Siacek et al. In 2014 with the first image summarization data set with 14 image collections, 100 features each, and 400 human summaries for each image collection via Amazon Talk, amounting to around 5,500 summaries. The evaluation was based on VROJ, based on features, image features. And another highlight of the work was two surrogate losses proposed as a part of VROJ, based out of VROJ, in their max margin loss. The idea for optimization was that you have a bag of submodular functions capturing different aspects of the problem. These could be coverage function, facility location, or feature-based or saturated coverage-based functions, and also diversity functions. The idea is to learn mixtures of submodular functions using max margin learning. That's exactly where the surrogate losses based on the evaluation of VROJ start playing a role. We present a generalization of the image summarization uh, that is privacy preserving and also query sensitive. We begin with privacy preserving component, which is basically defined as a conditional gain. The conditional gain of x given p, f of x given p, is basically f of x union p minus f of p. So this intuitively measures how different is the p from the x. And this makes sense for privacy preserving, because we really want the difference, or the x summary, to come out to be different from p and not reveal anything about privacy. Another function that one can define on any existing set function, including submodular functions, is that of mutual information, also called submodular mutual information. So given x comma q, say x and the query, the mutual information is defined as f of x plus f of q minus f of x union q. So note that this in contrast with f of x given p, which was basically f of x union p minus f of p. So while privacy look for the difference, the mutual information based function of f looks at the similarity between X and Q, and therefore it's natural to model the mutual coverage or share information between the extracted summary and the query Q. We can also generalize through this master optimization problem specified here on the right, if x comma q given p, and this can help capture both query and privacy. Now, how about optimizing? What are the properties of these different functions? So all these functions are non-negative and monotone in one argument with the other fixed. However, even if the function f is submodular, the query based mutual information function and the query plus privacy based conditional submodular mutual information function are not necessarily submodular in one argument, even with the others fixed. However, it turns out that several instantiations actually turn out to be submodular, and that's very interesting, which means that a simple greedy algorithm gives you 1 minus 1 over E approximation guarantee for the master optimization problem. So this is the unified modeling of the different flavors. You just set A, S and T to different values. For example, S if it's the entire universe and T is empty, then you get generic summarization. Query focused if S is Q and T is phi. Privacy preserving if S is the entire universe and T is the privacy preserving query. And update when S is the universe, and let's say T is an existing set which you want to update. And the very interesting examples of PSIM, we call this PSIM an acronym for parameterized submodular combinatorial information measures, and it turns out that this generalizes several existing functions. We also have several parameters here which look at, for example, the trade-off between coverage, diversity, representation, and so on. And this generalizes several past works including Rouge, which was referred to in the work of Siachik. For example, if this was the image collection, and let's say the function f was coverage function with the query set being, say, flower and car, what would we expect as a response? Well, since we are interested in covering flowers and cars, you would basically get one example of a flower and another example of car, not necessarily covering all flowers. On the other hand, if you were only looking at diversity, you would probably get one flower, one car, and then one natural scene, and also the human. If you're looking at only the relevance of flowers, you would get all the flowers. If you were looking at irrelevance, then you'd get diversity modulo the person, because person is what the privacy preserving pivot was. Now coming to video summarization of course brings in a lot more complexity beyond images. At the same time, with video summarization you have the additional advantage of some redundancy. So therefore the approaches there have been significantly specific to videos, and therefore somewhat different from what has been applied for image summarization. One of the oldest data sets was by Gigli et al. In 2015 with 25 videos and 390 ground truth summaries. The challenge has been consistency. So you'll find that across the users, it's very hard to insist that different users create the same ground truth summary or nearly the same ground truth summary by basically consistently picking up the same set of frames. And that's generally been also a quality criterion, inter-annotator consistency. Very difficult to attain though. These are other data sets, TV sum, MEDI summaries, and so on. The longest of them in terms of number of hours has been egocentric, which is a very different genre altogether, where you have camera mounted on the person's head, and then it's really capturing videos from the point of view of the person wearing the camera. So besides that, MEDI summaries are probably the largest, 9 hours, with 260 videos with duration of 1 to 5 minutes, an average 2.5 minutes. So the issues, they're either too few videos or too short videos or videos only of one type, which is egocentric. So we present a new data set and a new paradigm, which is visuosity, which has a significantly large footage, which is 71 hours with 67 videos with a duration of 14 to 121 minutes, an average of 55 minutes. The way the summaries have been developed for this wide spectrum um, is based on continuity, intent, and diversity, and it's driven by rich annotation so that different flavors of summarization and other tasks are supported. So the summarization makes the process of video summarization, ground truth generation, very objective. So this is the other motivation. No single right answer uh, is a characteristic of existing data sets. They're very context dependent, depend on purpose of which summary is required. A birthday summary will be very different from say a surveillance summary. Subjectivity, because two persons who are creating the ground truth may have very different preferences. Let's say even watching a TV serial like Friends, two summaries could be very different based on their likes. And also there's dependence on the high level semantics of the video. For example, visually same and semantically different versus semantically different and visually same. Um, a goal nearly scored versus a goal actually scored. Right? So visually they could be very same, but semantically mean very different. So again, highlighting the issue of consistency in human summaries, we'll find a number of human summaries which uh, basically agree on a particular segment is very difficult. While this is attested by previous work, we also found this. So for example, this here are two different snippets which have a agreement across different annotators. And now why do they agree? Well, it turns out that they agree because there's some objective criterion they seem to be implicitly following, which is that the goal scored. So why not go by annotations, which is goal scored? So to uh, circumvent this problem of no single right answer, learn from a combined reference summary versus learning from separate reference summaries. What we went about is creating a recipe for creating reference summaries of desired length, having different characteristics using annotation information. It's also very difficult to get summaries for long videos, whereas this objective criterion makes the process more seamless. Um, and we can evaluate video summaries with respect to reference summaries which have actually been created using objective criterion, Um, or you could use the annotations themselves, the indirect ground truth, to evaluate video summaries. So we propose a suite of measures that score a summary on different characteristics. And we could learn from a combination of loss functions instead of a single loss function, because we have a suite of measures to score the summary. So we have 67 long and diverse videos, 6 categories. As I pointed out, each category can have a very different flavor of summaries, and there are concept annotations for every shot. Here is what the annotations would look like. The concepts for each shot, indirect ground truth. There could also be mega events which span multiple frames or segments. And text annotations are better than scores or ratings, because ratings and scores can be associated with text annotations, but not vice versa. So we wanted the process to be as less lossy as possible, as objective as possible, have no chronological bias, capturing of semantic content through both text from importance and also diversity perspective. And obviously we want to be able to address a variety of problems which mean a variety of evaluation measures. This is our annotation tool where you could define keywords, identify keywords that exist in the shot, and basically as you populate the dictionary with new keywords, subsequent shots can avail of those. So the idea is to minimize redundancy, using synonymous keywords or key phrases. The user can also mark mega events for multiple snippets. For example, a snippet could be a transition, or it could be a part of a mega event. Now, what are the approaches for learning? Well, whether it's Visuosity or whether the other data sets, once you have ground truth, you could use any of the existing state-of-the-art. And Giggly is one such work, where they visualize a video as segments or circles. The circle size is an interestingness estimate, and whereas a spatial proximity is a measure of similarity. And the idea is combined objective of interestingness and diversity. The notion of interestingness is obviously modular. So therefore the size of the circle is basically a modular estimate, modular function. Here are some more details. Interestingness is simple sum of the scores of the elements, whereas representativeness, they used k-meroid objective, where you were minimizing distance of each segment in the video to the closest segment in the summary. And here's the segment in the summary, XS. They also brought in a notion of temporal representativeness, so that there is some smooth sail through the video, and that was a notion of uniformity. As pointed out earlier, most of these previous data sets have had ground truth summaries of different durations, and so therefore when the combinations of these three components, interestingness, representativeness, and uniformity, was computed, or rather learned, on summary lengths of 1 minute 20 seconds as against summary length of 2 minutes, you find that the importance given to representativeness has increased, and the importance to interestingness has decreased. Also a little bit more focus on uniformity because you have longer summaries. So this is where a bit of subjectivity does creep in. There have been many other attempts at video summarization which we will not get the time to go into. Basically learning DPPs, for example, video MMR, which was maximum marginal relevance, adaptation of an old idea applied original to images, and also text. Um, there has been work on use of LSTMs along with DPP. In fact, DPP improvised with LSTMs to get both sequential information as part of the summary as well as diversity that DPP is offered. Some people have also looked at other notions such as visually pleasing, coherence of the story, adaptive, user context driven summarization, and so on. Now, what forms a good summary really depends also on the domain. For example, um, you may be looking at diversity, objects or people tracks as against representation of faces and emotion, actions or scenes. So one might be interested in a mixture of diversity, representation and coverage. And here's a max margin framework that we proposed a couple of years back, where we look at the margin with respect to a whole bunch of submodular functions. And to evaluate video summarization, we look at positive ratings, negative ratings, and redundancy. And a loss function which encourages the positive ratings, penalizes negative ratings, and saturates redundancy. So here are some results on domain-specific video summarization. We find that if you were to basically look at the full joint submodular and modular, it does better than for a particular domain. Learning the weight combinations does best, and it also helps when you learn mixture from the same domain than across domains. So therefore it's useful to train. If you want to evaluate on birthday, you rather train on birthday. So this is birthday on birthday, entry exit on entry exit, and so on. Another important takeaway is that some of the top component features would intuitively correspond to the corresponding domain. For example, for birthday, we find that object features like cake, etc., become interesting concept and object features. Whereas in surveillance, diversity becomes very important. In the case of cricket, you would be interested in events. Now also correlating the top components. So let's say on the right hand side, we look at components with the highest individual score when optimized, as against the left where you have looked at the top components based on learned weights. And interestingly, we find that learning the mixture is a very reliable way of ensuring that you have right domain summaries, the right features triggering for the domain summary. There have been other approaches for video summarization through online video summarization, sparse dictionary learning, long short-term memory. We won't get into the details of these. These have just been provided for. Summarization has also found applications in other domains such as summarization of topic hierarchies. So let's say you have a hierarchy of topics from Wikipedia and you are interested in a subset of topics that cover the documents which are shown as leaves. Each of the intermediate nodes in this DAG covers a handful of documents. However, there's redundancy. There's no point in selecting nodes which subsume each other. So you might want to select either some abstract nodes or some specific nodes, or a combination of the two, such that you have maximization of coverage of the documents. At the same time, you're able to meet the budget constraint, that is you have a upper bound on the number of elements that get selected from this DAG. Now this has been studied in several works in the past. Here's a working example. You're given a document collection and you have a knowledge graph. You need to identify a subset of concepts shown here in the form of a word cloud from this large hierarchy or DAG. And as a concrete use case, you might have 150 technical documents, 100 subjects under science tracks, and how do you extract the subset of concepts? So here are statistics. Now with a knowledge graph like Wikipedia, this is Wiki 14, things have grown further, and as you can see, the number of categories are in the tens of millions. However, when you run the large number of categories through the pipeline of a method that invokes subset selection such that the subset is diverse, the subset has good coverage, and each node is of high quality, you would find that you can create this word cloud of 100 categories. The font size is proportional to the number of documents under that categories. And we did some manual comparison. Out of top 20 categories, 15 are in agreement with the actual true categories. And what are the submodular functions? Examples are coverage based, which helps select categories with good coverage of leaves. You could also have specificity. The more specific a category, the more you would like to select it. You would like the categories to be relevant, and you like the categories to be very clear. Now, all of these can be modeled as modular functions. Subset selection has also been applied for other tasks such as pattern extraction, let's say in domain machine translation. Now these patterns also form a directed acyclic graph where you could have abstractions in the form of category 1 and category 2 and category 3. Now what is the right level of abstraction of phrases? How should we interleave these abstractions along with the actual lexical entities that are those are the words? Again, this is a search problem over a very large search space. Notions of quality, which is quality of individual patterns and quality of set of patterns, both are required. When it comes to quality of set of patterns, coverage, diversity, and the kinds of measures we have talked about, some of them not being submodular, for example, disparity, become very important. So here is a summary. We talked about data subset selection and active learning, and three different components therein: feature selection and compression, again information theoretic, weak submodularity, and categorical feature compression. We concluded with learning to compose features combinatorially. We talked also about the advances in a very related area, which is submodular minimization, also convex relaxations that have found use in feature selection. And finally, we concluded with applications of subset selection in video, image, and text summarization, including summarization of topic hierarchies and DAGs. Thank you very much for your attention.